Hi everyone. In this lesson, we'll use the concept of infinity to talk about derivatives. So if you remember, the derivative was the concept of x-raying a shape, right, and splitting it up into little pieces. Well, let's take that concept and play with it a little bit. One analogy I like to use is imagine that you're a doctor trying to measure a patient's heart rate. So what you do is you take a guy, put him on a treadmill, and get him running. You want to measure his heart rate when he's exercising. So the patient's running, and you've put all these wires and electrodes on him, and you get a reading, like, I don't know, 180 beats per minute. So that's got to be his heart rate, right? 180 beats per minute? Well, not exactly, because that's his heart rate when you have a doctor looking at him, when he's on a machine exercising with all these electrodes on top of him. So the problem is the electrodes are kind of adding an interference there, right? Let's say the electrodes are getting tangled on themselves. So the presence of the electrodes are actually changing what they're measuring. And, it's kind of a weird thing because we need the electrodes to measure something. But given that they're there, they're also adding their extra effect. So we need to kind of remove it at the end. And so, for example, if we saw that the person had a heart rate of 180 beats per minute, we might say, well, you know what, we've done some experiments and it turns out that the electrodes are actually adding 5 beats a minute of stress. So we take the 180 beats per minute, remove the 5 beats per minute of stress, and then we get 175. So the key there is we make the measurement, but then we need to remove the effect of our little instrument on the measurement. Well, for the derivative, the dx that we use is actually like that little electrode being stuck onto the function. So as you saw before, when we try to grow a square and we sort of follow this dx equals 1 pattern, we get these two strips and we also get a corner piece. Now the tricky thing is to realize, well, what's real and what's not real? These two pieces are kind of attached to the main function. They were sort of formed by the main function growing. But this corner piece here, that was actually formed by one of our measurements or one of our changes interacting with another one of our changes. And so my intuition is that that's a little bit like one of the electrodes getting tangled up on itself. We see a reading here, but that's really this kind of initial measurement interacting with this other one, and we probably shouldn't include it. Now, in calculus, there's a few different ways to kind of throw away that little corner piece, that's the interaction. And there's theories about limits, there's infinitesimals, and we can go into that later on. But the key is to realize that certain parts of this measurement are kind of real and certain ones need to be removed. And there's various theories about how to do that. And let's just, for today, we'll use the limit theory. And again, we don't need to get into it too much, just the idea that we can remove pieces that seem to be artificial. Now, as we saw before, we had a process for finding the derivative, right? We make a change of dx, we get the new amount, subtract the old amount, and then take the ratio. The last step is to actually make that little change into nothing. So this is sort of taking the limit as dx goes to 0. Don't worry about the terminology there. Just imagine that once we've made this change, we want to sort of remove the effect of these sort of artificial interferences. So let's just take it through an example. We'd start off with a function like x squared. We make the change. That means we take x to x plus dx. And when we do that out, we get this, x squared plus 2x times dx plus dx squared. And the difference is 2x times dx plus dx squared. Now we take that ratio, right, because we want the kind of output change to input change. So we divide by dx, and we get 2x plus dx. That's the amount of change that we expect, and that's pretty much what we see here, 2x plus dx. The last step is to actually throw away the measurement artifacts because dx is sort of the presence of our instrument. We want to remove any evidence that we even use an instrument, right? We don't want the wires to get tangled. So we kind of remove any dx that we see left over, and that becomes 2x. And as you can see, if we do it on the computer here, Wolfram Alpha returns the derivative of x squared is exactly 2x, and that's what we found on ourselves. There's a few little subtleties there, which you can see in the article, but the key idea is to essentially make the measurement, to look at it, and to realize that this little corner piece is an instrument artifact and doesn't really exist.